Welcome to our solar training program. Solar power is very scalable, and so many lessons in residential material selection also apply to commercial projects and utility scale. So, this is a good starting point as any to increase your knowledge of the solar industry. Feel free to ask questions and use the chat widget to communicate. In the next 2 hours, we're going to review modules, inverters, and solar racking terminology, as well as balance of system material. We'll also talk about supply chain, such as how installers purchase material for small projects. This class will stay away from design scope. There are other classes we offer that cover this material, which you can ask about, but let's go ahead and get started with this. The solar industry calls these solar modules instead of solar panels, and we will use the terms interchangeably in class, but technically we call them solar modules as electric code already uses the term panel to describe other important things. And also, the term module does mean something specifically. An electric service panel holds breakers that distribute power to a home, including the solar array. A roofing panel can be the section of roof that a solar array sits on top of. So the term solar panel already has other uses in electric code. The term module in electric code is used specifically to refer to a grouping of individual cells. So you might have heard of a battery cell. A 12-volt battery might be a single circuit of six 2-volt cells wrapped up in a module. Similarly, a solar module or solar panel is a grouping of individual cells. Most residential solar panels are 60 cell panels, and most utility scale solar panels are 72 cells. So, counting the cells here, there are 1, 2, 3, 4, 5, 6, and then along the length, there are 1 through 12. 6 times 12 is 72, and so this is a 72 cell solar panel. This solar module has a black backsheet instead of a white backsheet, but a trained eye can still count the cells. We have 6 cells across, but this module is a little bit shorter than the 72 cell module, only having 10 cells down. That makes it a 60 cell solar module. And the difference between a residential 60 cell panel compared to the utility scale 72 cell panel is these extra 2 rows of cells, which give the module a little bit more height, weight, and voltage. A larger panel, such as the 72 cell panel, means slightly more bang for your buck all the way through the project. But the problem with 72 cell panels is that they're a little too tall and a little too heavy for one person to safely handle on a slanted roof. So residential rooftop solar will have the 40-pound, 3 1/3 by 5 1/3 foot, 60 cell solar panels, typically, again, because they're easier to manage on a roof. On ground mounts or flat commercial projects, the larger 72 cell panels have slight cost advantages. A few specialty module manufacturers might deviate from these standards as well, and 72 cell modules are allowed on residential roofs. They're just a little harder to manage. So a solar panel is about 3 1/3 feet by 5 1/3 feet. Maybe it's a little different than that, but that's an easy enough number to go by. It's just small enough for one person to pick up and walk around with. The 72 cell panels used in utility scale projects are 20% larger, having 20% more cells. They'll weigh 20% more as well and have 20% more voltage too. And so a 72 cell panel can be a little bit over 6 feet tall, still 3 1/3 feet wide. But that extra height means it gets a little hard to manage on a slanted roof. A 60 cell solar panel weighs about 40 pounds, and so a 72 cell panel weighs about 50. Silicon for solar panels is grown as a rectangular sheet known as polysilicon, or it is grown in a cylinder and sliced like a salami called monosilicon. Whether they're cutting the rectangle of silicon or the cylinder of silicon, the interior of the silicon is more pure than the edges of the silicon crystal. And now manufacturers sort the more efficient cells from the lower efficiency cells, creating higher efficiency solar panels and lower efficiency solar panels. Cell sorting is one of the many reasons solar panel efficiency has increased dramatically over the past few years. With different cells going onto different modules out of the same production batch, that is why on a module specification sheet, there will be different specifications for slightly different solar wattages, all of which have the same dimension. The cell sorting creates all these different wattages out of the same production batch, and they're priced differently as well. Monocrystalline solar is slightly better than polycrystalline silicon due to these slight differences in the manufacturing process, but they're like siblings born in the same year in that they're very similar, if not quite twins. Futuristic thin film solar panels, such as translucent solar panels, do exist, as do solar shingles, but all that stuff is a very small section of the solar market. Silicon is the clear market leader right now at a couple bucks a pound. So, on a side note, if a solar panel weighs 40 pounds and a pound of silicon costs $1, there's approximately $40 worth of silicon in a $150 solar panel. Solar module efficiency is the percentage of energy that hits the surface of the panel versus how much electricity flows out the back side of it. An impressive 20% of natural sunlight can be converted to electricity at its standard test condition, and that number continues to climb. Today's solar panels capture almost twice as much electricity as the technology 15 years ago. Solar panels which are still producing power today. So scientists themselves have underestimated how much electricity can be squeezed out of the annual incremental improvements in solar module design. For example, a recent advancement in silicon is called PERC, which makes the bottom of the solar cell more shiny. This additional reflection increases the total solar panel efficiency by 1%. Let's get back to the basics with module specification sheets. The module power rating is how many watts of power the panel will output under certain lab test conditions. This information can be used for pencil and paper design, but nowadays most design decisions are guided by computer design software. This solar panel is an older model, and so it has slightly lower wattage than most solar being installed today. Most 60 cell solar modules today are around 350 watts, just under 10 amps and 40 volts. MP or MPP stands for maximum power or maximum power point. Basically, the maximum power point is the operating voltage and the operating amperage rather than the solar maximum voltage and maximum amperage. The maximum amperage is the short circuit current, and the open circuit voltage is the maximum voltage, how high the voltage would be if it were fully energized without being under any load at all, like a light switch turned off with electrical power on one side of the switch and just metal connected to the ground on the other with nothing but voltage potential in between. The maximum voltage and amperage are used in system design rather than the operating voltage or amperage. A solar array may be designed for 600 volts, but it'll operate at a lower voltage. All the figures given on a module specification sheet are listed for a standard lab test condition. Just like a car gets a mile per gallon rating, the solar panel gets a wattage rating at a standard test condition. But solar performance changes hourly as well as seasonally as the sun changes position across the sky. Overcast days will diffuse sunlight, but only sometimes is this diffusion enough to turn the solar panels off, or the numbers can jump around on a partly cloudy day. So the numbers on the module spec sheet are just a starting point, and how might they compare with solar performance on a normal day? The standard test condition amount of sunlight is 1,000 watts per meter square. There's a free public software called PV Watts, and as an example, I'm going to pull up Biloxi, Mississippi. And this is a PV Watts example for a 1 kilowatt solar array in Biloxi, Mississippi. Like other coastlines, Biloxi gets better production than slightly further inland because clouds tend to blow over the coast rather than to stand still. Anyway, at the end of PV Watts, the hourly results provide an estimate of the actual amount of sunlight that will hit the surface of a solar panel throughout the day and throughout the year. PV Watts takes into account array tilt and orientation, and for this 18-degree tilt south-facing array, the array irradiance is listed on the spec sheet as the lab condition of 1,000 watts per meter squared. And that's equivalent to the high temperature on a cold spring day. Compare this winter day in PV Watts, the solar array only gets 360 watts per meter square of sunlight. That's only 30 to 40% of the sunlight used in the lab test. And so the solar array only produces 30 to 40% of its rated capacity on this particular cloudy winter day. On a sunny day, still in winter, the array gets up to 640 watts per meter square. Moving into July, the temperature begins to impact the array by 10 to 20%. So even if it has full exposure to 1,000 watts per meter squared sunlight, the temperature drags down the performance of the array. So calculating solar performance isn't as simple as taking the size of the solar array, multiplying by the hours of daylight, and then getting the amount of energy the solar array will produce from it. The wattage rating on the module assumes that 1 hour of daylight is 1,000 watts per meter squared, but actual daylight hours rarely get up to that amount of sunlight shining directly on the solar panel. So a software like PV Watts is needed in order to estimate solar production. It's easy to use and covered in some of our other classes. Then there's this other part of standard test condition called the module surface temperature, and that's done at 25 degrees Celsius. So how does that compare to actual rooftop temperature? 25 degrees Celsius is equivalent to a 77-degree Fahrenheit day, and so how hot does it get on the roof when it's 77 degrees Fahrenheit out? Again, PV Watts comes in handy. It provides ambient temperature and module temperature, and it shows how to convert from ambient temperature to module temperature. But the standard test condition is done at module temperature. And so at a 77 degree Fahrenheit module temperature, the standard test condition is equivalent to the temperature of a 60-degree day outside, which is not very typical weather for most of the year. On the module spec sheet, there are temperature coefficients to show how voltage, amperage, and power are impacted by temperature. For example, if the rooftop is 50 degrees Celsius and standard test condition is 25 degrees Celsius, multiply the difference of 25 degrees by 3.4% temperature coefficient, and that produces an 8 to 9% loss of voltage. The temperature coefficient of amperage is the opposite of the temperature coefficient of voltage. It has a positive sign, but the temperature coefficient of voltage has a negative sign. So whereas voltage will decrease with temperature, amperage will increase with temperature. That's worth pausing to memorize, that voltage decreases with high heat and amperage increases with high heat, having the opposite effect. But if you're having problems understanding what voltage and amperage are, I recommend starting with a volt times an amp is a watt. In other words, power is the multiplication of voltage and amperage. So voltage and amperage are different things that make up power, and we'll leave it at that for now. Bring us back to our temperature coefficient discussion. The temperature coefficient of power is a negative 0.4% per degree Celsius. So at a surface temperature of 50 degrees Celsius, there is a 25 degree difference between that and the standard test condition. So a 25 degree temperature differential multiplied by 0.4% correction factor means a 10% loss of power due to temperature alone on this, moderately hot summer day. Sunlight, also known as irradiance or insolation, has a linearly proportional effect on solar module power. So if the air has twice as much sunlight in it, a solar panel will produce twice as much energy minus any temperature effects of the array or minimal amounts of energy required to start up the array. This is our open circuit voltage with all the voltage and no amperage. The short circuit current is the opposite of open circuit voltage with all current and no voltage. So the bend in this curve here is the maximum operating power of the solar panel with the right level of voltage and amperage to produce the most amount of power under normal operating conditions. So the solar panel will operate at a little bit less voltage than its open circuit voltage and a little less amperage than its short circuit current. Adding any electrical load to voltage will reduce system voltage because electricity is not infinite. Too large a load on too small a battery will lower the voltage to the point where it can't deliver any power. Too much load on an electric grid can lower the grid voltage as well. But normally our electric grid is very large, and so it provides us with a stable voltage because our loads are small and the grid is large. The solar panel too has an ideal operating voltage and amperage, and in the past, this would lead to a very difficult discussion about keeping the solar panel away from shade at all cost. Maximum power point tracking, how the inverter operates the module at its voltage and amperage level, will reappear in the inverter discussion. Solar panels are designed to go outside. Manufacturers have a hail test designed at 1-inch thick hail at 45 miles an hour. And so a solar panel is similar or tougher than most roof material. Installed correctly, solar can strengthen and protect the roof, but solar isn't bulletproof. It is strong and durable enough to give a false sense of security. It's a quality object, something you can throw in the back of your truck and drive down the road and have it be okay. By itself, it will not likely break or shatter. Even if you drop it flat on its face, it might be okay. It's durable and designed to face the elements. The specification sheet will tell the physical load data such as snow load and wind rating. The panels are tested again for hail impact. They might have a positive, tolerance or a plus or minus power tolerance. This power tolerance has significantly improved over the years. All of these numbers are fairly similar throughout the industry. A particular manufacturer might have a patent on one unique ability to improve module production, but for the most part, the solar module features are more common than specialized. Some manufacturers provide different module frame thickness to choose from. So in hurricane zones, you can get a more robust module. Sometimes this information can only be found in the manufacturer installation manual. So here's an example that illustrates various ways to install this particular manufacturer's solar panel to a rack. It provides different wind load and snow loads based on how the module clips are installed relative to the module frame. Also shown is a technique of adding an additional rail for more reinforcement, such as to meet hurricane wind load requirements. There's 24 mainstream solar manufacturers still in this industry, so by and large, module quality is very good. The type of frame, the color of the frame, the gauge of the wires coming out of the back of the panel, all of that information can be useful to know. One of the notable industry standards is the MC4 connector coming out the back of the solar panel. A common point of system failure is the field-made MC4 connector. Even when doing things correctly, it can be easy to confuse the male and female housings and metal connection tips of the two different connectors. Furthermore, the connector itself should not be exposed to any direct rain, such as dripping down in between the module frames or accumulating water. So attention must be paid with cable management and locating these connectors in addition to just making them. Finally, they click together with a nice snap. Even the information like how much length of cable comes off the back of the module for these MC4 module whips plays a role in advancing solar design, such as how to route the cable underneath the solar panel to make up the extra slack. This is the stuff that solar installers take pride in, having that extra slack tucked out of the way in a workmanlike manner as to not attract nuisances like squirrels or debris. Since we're starting with material selection, a more advanced material selection note is to review the voltage ratings on those MC4 connectors we were just talking about. MC4 connectors are standard in the industry, and some field-made connectors meet up with the plugs that come out the backside of the solar module. While these connectors are universal, not all are rated for 1,000-volt commercial systems, so that's good to check, particularly when you're installing a commercial solar array. The detail on a module spec sheet can assist racking planning. Some manufacturers will hollow out this piece of metal in the module frame to save a little money. The US manufacturer SolarWorld does this with some of their panels. On standard solar, though, the robust module frame allows the racking underneath to run in portrait or landscape orientation. And so the solar panels can be designed in both orientations unless they have a weaker module frame.